Hi everyone, welcome to Mathly. Today we are diving into support vector machines or SVM, a powerful machine learning algorithm used for classification and regression tasks. SVM is widely used in image recognition, text classification, medical diagnosis, and more. Unlike traditional classification algorithms, SVM finds the best decision boundary that separates different classes with the maximum margin. But what if the data isn't easily separable? No problem. SVM uses something called the kernel trick to handle even the complex datasets. And the best part, I'll show you how to use orange data mining to apply SVM step by step. Let's dive in. Imagine you're a teacher trying to separate two groups of students based on their exam scores and attendance. You want to find the best possible dividing line that separates high-performing students from low-performing ones. That is exactly what SVM does. It finds the optimal boundary between different categories while maximizing the margin between them. SVM is a supervised learning algorithm used mostly for classification problems. It works by finding the best hyperplane that separates data points belonging to different classes. The closest points to the boundary are called support vectors, and they play a crucial role in defining the model. Even when data isn't perfectly separable, SVM can transform it into a higher dimensional space using the kernel trick. This makes it possible to classify even complex datasets. SVM is widely used in facial recognition, cancer detection, handwriting recognition, and more. Now let's see how it actually works. Support vector machines work by finding the optimal decision boundary that separates different classes while maximizing the margin between them. Let's break it down step by step. Step 1. Finding the best hyperplane. In a simple classification problem with two classes, support vector machines aim to find the optimal decision boundary, known as the hyperplane, that best separates the two categories. Unlike other classifiers that might just draw a line to separate classes, SVM maximizes the margin between the closest data points of both classes. The data points that are closest to this hyperplane are called support vectors. These points play a crucial role in defining the boundary as they directly influence its position. The larger the margin between the support vectors and the hyperplane, the better the model generalizes to unseen data. Step 2. Handling non-linearly separable data, kernel trick. If the data is linearly separable, a straight line in 2D or a plane in 3D is used as the hyperplane. However, in cases where the data is non-linearly separable, SVM uses the kernel trick to project the data into a higher dimensional space, making it possible to draw a clear boundary. In such cases, SVM uses kernel functions to transform the data into a higher dimensional space where a hyperplane can separate it. We won't go too deep into the concepts, but here's a quick look at some common kernel functions. Linear kernel, used when data is already linearly separable. Polynomial kernel, captures more complex relationships by considering combinations of input features. Radial basis function kernel, maps data into an infinite dimensional space, making it effective for highly nonlinear data. Step 3. Making a prediction. Once the optimal hyperplane is found, SVM classifies new data points based on which side of the boundary they fall. If a new data point falls on one side, it's classified as class A. If it falls on the other side, it's classified as class B. As an example, let's consider face recognition. Imagine your phone uses face recognition to unlock. How does it know whether the face in front of the camera is yours or not? Step 1. Extracting facial features. The phone analyzes facial features like eye distance, nose shape, and jawline. Each face is represented as a data point in high-dimensional space. Step 2. Finding the optimal boundary. SVM finds the best hyperplane that separates your face from others. The phone trains on multiple images of your face and other people's faces. Step 3. Unlocking decision. If the detected facial features fall on your side of the boundary, the phone unlocks. If not, it stays locked. To put it simply, support vector machines finds the best boundary that separates different categories by maximizing the margin between them. It's effective, reliable, and widely used for tasks like image recognition, text classification, and medical diagnosis. Now, let's see it in action using Orange data mining. Now, let's take a look at how we have set up our workflow in Orange data mining to perform support vector machines on the Universal Bank dataset from Kaggle. First, I have imported the Universal Bank dataset from my local machine. This dataset contains financial and demographic information about customers. The objective is to build an SVM classification model that predicts whether a customer is likely to accept a personal loan offer from the bank. After loading the dataset, I have used the data table widget to inspect the data. Here we can see the key attributes of each customer. ID, a unique identifier for each customer. Age, the customer's age in completed years. Experience, number of years of professional experience. Zip code, customer's residential zip code. Securities account, whether a customer holds a securities account, yes or no. CD account, whether the customer has a certificate of deposit account. Online, whether the customer uses internet banking. Credit card, whether the customer owns a credit card issued by the bank. Personal loan, this is the target variable indicating whether the customer accepted the loan offer. The dataset contains 5,000 instances, giving us enough data to train and test our model. By analyzing these features, we aim to predict customer behavior regarding personal loan acceptance. Before training our model, we need to split our dataset into training and testing sets. This is where the data sampler widget comes in. It helps us randomly select a subset of data for training while keeping the rest for testing. I have chosen the fixed proportion sampling type, meaning a predefined percentage of the dataset is used for training. I have set the proportion to 80%, meaning 80% of the data, or 4,000 instances, is used for training the model, and 20% of the data, or 1,000 instances, is reserved for testing the model's performance. With this sampling setup, we ensure that our SVM model is trained on sufficient data while still being tested on new unseen cases to measure its predictive accuracy. After splitting the data, we need to train a classification model. Here, I will be using the support vector machine (SVM) for this classification and regression task. Here, for the SVM type, I have selected the standard SVM option, meaning the model will find the best possible decision boundary to separate the two classes, which are loan accepted versus loan not accepted. And the cost is 1. This controls how much the model tries to avoid misclassifying training samples. A higher C results in a stricter boundary, while a lower C allows more misclassifications but generalizes better. The kernel trick allows SVM to work in a higher dimensional space without explicitly transforming the data. I have selected the polynomial kernel, and this kernel is effective when relationships between features are nonlinear. Let's take a look at optimization parameters. Numerical tolerance is 0.0010. This controls the precision of optimization. Lower values makes it more precise but computationally expensive. Iteration limit is 100. This limits the number of iterations to prevent excessive computation time. This configuration allows the SVM model to effectively learn patterns in the dataset and make predictions on unseen data using a polynomial decision boundary. Once the support vector machine model is trained, it is crucial to evaluate its performance. The Test and Score widget in Orange Data Mining provides a detailed assessment of how well our model predicts whether a customer will accept a personal loan or not. The model is tested using 5-fold cross-validation, meaning the dataset is split into 5 parts, and the model is trained and tested multiple times to get a more reliable accuracy estimate. Let's take a look at the performance metrics. The area under the curve score is 0.926. which indicates the model's ability to distinguish between customers who will accept the loan and those who will not. The classification accuracy is 0.934, meaning that 93.4% of the predictions were correct. However, accuracy alone is not always a reliable measure, especially when dealing with imbalanced datasets, so additional metrics must be considered. The F1 score of 0.936 represents a balance between precision and recall, ensuring that the model performs well across both measures. The precision score of 0.937 means that out of all customers predicted to accept the loan, 93.7% were correct, which reduces false positives. Meanwhile, the recall score of 0.934 indicates that out of all customers who actually accepted the loan, 93.4% were correctly identified, minimizing false negatives. Additionally, the Matthews correlation coefficient or MCC is 0.639, which is a more reliable performance indicator, particularly when dealing with imbalanced datasets. MCC value ranges from -1 to +1, where +1 represents a perfect classifier, meaning the model maintains a strong correlation between predictions and actual outcomes. These results confirm that the SVM model with polynomial kernel is highly effective, providing a well-balanced classification with strong predictive power. To further analyze the model's performance, I have used the confusion matrix widget, which provides a detailed breakdown of correct and incorrect predictions. This helps in understanding where the model performs well and where it might need improvement. In the confusion matrix, the rows represent actual classes, whether a customer accepted the loan or not, and the columns represent predicted classes, which is what the model predicted. The top left value of 3,466 represents true negatives. These are cases where the customer did not accept the loan and the model correctly predicted that they wouldn't. The top right value of 145 represents false positives. These are cases where the model incorrectly predicted that the customer would accept the loan when they actually didn't. The bottom left value of 117 represents false negatives. These are cases where the model failed to identify a customer who actually accepted the loan. The bottom right value of 272 represents true positives. These are cases where the model correctly predicted that the customer would accept the loan. This confusion matrix indicates that the model performs well overall, as the majority of the predictions are correct. However, there are still some misclassifications, particularly in the false positive and false negative categories. While the false positive count suggests the model occasionally predicts loan acceptance incorrectly, the false negative count means that some customers who would have accepted the loan were missed. These insights highlight the strengths and limitations of the model, reinforcing the importance of precision and recall when evaluating classification performance. I have added the test data widget and connected it to a data table widget. This setup allows me to inspect how the model classifies new and unseen samples. This step helps assess how well the trained SVM model generalizes to new data. By checking the predictions, I can determine whether the model maintains high accuracy or if any misclassifications suggest potential areas for improvement. Finally, I have used the prediction widget to compare the model's predictions with the actual values from the test dataset. The output displays the actual personal loan status from the dataset and the predicted value from the SVM model in the leftmost column. Upon inspecting the predictions, we can see that all instances are correctly classified. The model has successfully predicted whether each customer accepted the personal loan offer without any misclassification. This indicates that the SVM model generalizes well to unseen data and effectively captures patterns in loan acceptance behavior. The high accuracy of predictions suggests that the chosen features and model parameters are well optimized for the classification task. And that is our complete workflow for training and evaluating an SVM classifier in Orange Data Mining. We successfully loaded the dataset, pre-processed the data, trained the model, assessed its performance, and tested it on new instances. The SVM model demonstrated strong predictive accuracy, making it a reliable tool for identifying potential loan acceptance patterns. And now, let's look at some real-world usage scenarios of this model. Support vector machines are widely used in real-world applications where fine classification and decision-making are crucial. Let's explore some key areas where SVM plays a significant role. Handwritten digit recognition. Ever wondered how your phone or tablet recognizes handwritten text? SVM is a key algorithm behind handwritten digit recognition systems, such as those used by postal services to sort mail automatically. It learns to differentiate between numbers by identifying the best boundary between different digits, ensuring accurate classification. Medical diagnosis and cancer detection. In the healthcare field, SVM is used to classify medical images and detect diseases like cancer. For example, SVM helps in analyzing MRI scans to distinguish between benign and malignant tumors based on pixel intensities and patterns. This aids doctors in making early and accurate diagnoses. Facial recognition in security systems. Many security and surveillance systems rely on SVM for facial recognition. The algorithm is trained to recognize facial features and distinguish between different individuals. Whether it's unlocking your smartphone or verifying identity at secure locations, SVM helps in accurate and efficient facial detection. Text and email classification. SVM is also used to classify text in applications like email filtering and document categorization. It helps email servers like Gmail detect spam by analyzing keywords and patterns in emails. Additionally, SVM is used by news platforms to automatically sort articles into categories like sports, business, and entertainment. Stock market predictions and financial analysis. Investment firms and financial analysts use SVM to predict stock price trends based on historical data. By analyzing past fluctuations, trading volume, and market indicators, SVM helps identify patterns that suggest whether a stock is likely to go up or down, assisting investors in making informed decisions. From recognizing handwritten digits to diagnosing diseases, detecting faces, classifying emails, and predicting stock trends, support vector machines are a powerful and versatile tool in machine learning that plays a crucial role in various industries. And that is how you can use Orange data mining to apply support vector machines in real-world scenarios. We explored how SVM finds the best decision boundary, how it works with different types of data, and how it's used in fields like healthcare, finance, and security. If you found this video helpful, don't forget to like, share, and subscribe to Mathly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.